Hey, this is Christian Hulteberg again, coming to you with a final webinar on catalysis. Today it's going to be focused on deactivation. As always, I represent Hulteberg Chemistry Engineering, specializing in heterogeneous catalysis, working all the way from research through development to upscaling, and we help everybody that wants from idea to implementation. The outline of the day will be that we start with a quick introduction to the area of deactivation. Then there will be specific topics around poisoning, sintering, and fouling. And finally, a few slides on selectivity and some conclusions. And as always, at the end, there will be further reading. So deactivation is basically the loss of activity and/or could be also impacting selectivity. And the time scale of deactivation can range from seconds into years. And if you look at different unit operations in a refinery, the fluidized catalytic cracker, for instance, would be deactivating in seconds, where you have a very rapid carbon buildup. And that's also why we do it in fluidized mode. Steam reforming for hydrogen generation would then, on the other hand, only require replacement every 3 to 5 years, something like that. So depending on how fast your deactivation is, you actually choose how to design your system. So if you have very quick deactivation with carbon buildup, for instance, you need to replace the catalyst rapidly, then fluidized catalysts or fluidized reactors are more suitable. For catalysts that do not do rapid deactivation, fixed bed is the most common one. Deactivation can have many different causes. One major cause of deactivation is over temperature excursions, when you allow more or higher temperature in your reactor than it was intended. It can also be changes in inlet composition, so not only changes that influence temperature, so too much oxygen in a combustion reaction. It can also be that you introduce too little steam, for instance, that would then make carbon formation more of a problem. And another thing that is really important is process hygiene. So upstream purification. How well do we remove chlorine, fluorine, and other contaminants before they hit the catalyst bed? That's also really important. And to me, deactivation is what happens after the first initial lowering of activity. When you start working with a catalyst and it's fresh, there will be some initial decrease in activity. There will be recrystallizations. The metal clusters on the surface will find their final configuration combining with each other. And then after 50 to 100 hours, that shakedown period is sort of over, and this discussion is around what happens after that. And we divide deactivation into 3 different categories: chemical, thermal, and mechanical. And then you can go on and you can break down each of these categories in finer bits. So poisoning, for instance, is a chemical mode of deactivation. Sintering is thermal. Fouling can be either mechanical or chemical. Then you have attrition or crushing of the catalyst, which is a purely mechanical deactivation measure. It's quite common when you have switching between hot and cold states that you get contraction of metal and crushing of the catalyst. Chemical deactivation is also when you have your active phase turning into vapor and transported out of your catalyst, as well as other vapor-solid or solid-solid reactions that are chemical. We'll look more closely at poisoning, sintering, and fouling today. And just to give you an overview, these are depicted here. So first, we have fouling, which is when you have coverage either of a complete pore or a part of the surface. So fouling is when that is overflown. The surface underneath becomes inaccessible to the gas phase. It can be either formed in situ, so like carbon formation, but it can also be transported in via ash, for instance, in biomass combustion reactions. Then you have poisoning, when you have some compounds sticking very strongly to your metal. In this case, it's a supported metal catalyst, and can be a platinum, for instance, and you have sulfur, oxygen, carbon monoxide sticking very hard to the material. And if there's something there, there won't be space for other molecules to land and react. Sintering, the last category, is either surface area reduction due to growth of the crystals of the surface, like this, either atomic migration or crystallite migration, or indeed it can be that the support closes up on itself and renders part of the catalyst inaccessible. But let's start with poisoning. Poisoning is a potentially irreversible interaction between a gas phase molecule and the active phase. It can be selective or non-selective, and it's definitely different if the catalyst is metallic or non-metallic. So if we look at metal catalysts, they're normally deactivated by group 5 or group 6 elements: nitrogen, phosphorus, arsenic, antimony, oxygen, sulfur, selenium or tellur. And these compounds are, so these species are deactivating the catalyst, but also compounds of the catalytic toxic metals like hydrogen sulfide or other sulfur components will also introduce deactivation, but also others compounds that contain multiple double bond, like carbon monoxide and carbonyl nitrile, things like that. And the deactivation of metal catalyst is usually due to pairing of unshared electron pairs. So these unshared electron pairs, they do very nice and very strong chemisorption to the metal. And when it's very strongly adsorbed, it won't desorb and it won't leave space for other materials to react on the surface. But it's not just that it blocks one single site. Since it's strongly electronegative, it will also impact other active sites around it. So sulfur, for instance, adsorbing on a nickel surface will actually impact not 1 but 8 active sites for steam reforming. So there are effects not only in the closest vicinity but also a bit away from the adsorbed molecule. For heavy metals, it's actually the 5d orbitals that are doing the toxicity. So if there are no 5d orbitals or uncoupled 5d orbitals, there will be no poisoning effect. So if we break it down, we have most of the active phases here in the middle: nickel, copper, iron, cobalt, ruthenium, rhodium, platinum, palladium. But to the far right, we actually find most of the catalyst poisons, and this is where we have the strongly electronegative species. If we then look at non-metallic catalysts, they're actually deactivated by their counterparts simply. So if you have an acid catalyst and you feed something that is basic, they will strongly attract and they will cancel each other out. And the same goes for basic catalysts, where an acid will knock out the active function of the basic catalyst. There are also examples of bifunctional catalysts where you have one acid site doing cracking and one supported metal site doing hydrogenation reactions, for instance, like in reforming catalysts. And there you can see that you can knock out one or the other function. But we also see effects on the catalyst bed. So we see two types of behavior, and depending on the behavior, we can also make statements on how strong the poisoning effect is on the catalyst. So to the left, we have one behavior with a fresh catalyst. And if we have something that strongly, irreversibly poisons the catalyst, this reaction front will have the same shape, but it will move forward through the catalyst bed until you start seeing breakthrough in the end. So you will have controlled linear deactivation. If it's non-permanent poison, you will see not a moving of the catalyst light-off profile, but more of flattening. So if it will be more adsorbed in the beginning, but after a while it will transport further down into the catalyst bed and it will spread out and lower the activity throughout. So the catalyst profile, or the reaction profile over the catalyst bed, can tell us if it's irreversible or non-permanent poisoning. All right, sintering. Sintering can be either the active phase or the support, but in both cases we lose metal surface, either directly, like here, where we get atomic migration or crystallite migration of several small crystal structures forming larger crystal structures. But it can also be that the porous support closes up on itself and encapsulates the active metal. And if you look at the support sintering, it's actually caused by crystal growth, and the increase in size is done to lower the surface free energy. So it's governed by thermodynamics, and you can, if you like, illustrate it in theory with a material, one which has a melting point of 1200 degrees and one with a melting point of 2000 degrees. And look what happens theoretically over 6 months of sintering. And you can see that the resulting theoretical crystallite size differs quite significantly between the two. So to get 10 nanometers, you need to be at 125 degrees for 6 months with the 1200 degree C material, but 570 for the 2000 degree C. And to achieve 100 nanometers, it's 325 versus 730, and so on. So you see that the melting point of the material theoretically does influence the deactivation, but then there is also kinetic effects and other things involved. So this is only an illustration. And practically, the support sintering is influenced by two things. It's temperature, but it's also the reaction atmosphere. The most important thing always is temperature. So the higher the activation energy, the deactivation by sintering of the support requires rather high activation energies, which means that you need to increase temperature quite significantly. And there is a temperature for each material below which you can't see any substantial sintering. We call it the Taman temperature, and it's about 40 to 50% of the absolute melting point. But if you have the same temperature, you will see higher sintering rates, most likely when you have oxygen and steam present, because those promote the sintering reactions. You will, on the other hand, see less sintering if you have hydrogen and nitrogen present. Sintering of the metal crystallites, on the other hand, they can occur by two different mechanisms. It's either atomic migration, when you have so either atomic migration or crystallite migration, and they both form these larger crystallites. And you can see that the surface area on these two here is larger than this one here. So the loss of surface area gives us the loss of active phase for the reaction to happen, and that's also where we see the loss of activity. And to do this crystallite migration, that's actually, again, coupled to the Taman temperature. So when we have about 40 to 50% of the absolute melting point, we have the crystallites in sort of a liquid, quasi-liquid state, and they are more prone to moving. And that's when you see entire crystallites moving around, meeting each other, and combining to lower their energy. And for the atomic migration, it's actually a lower temperature that is required. You need to go to about 30% of the absolute melting point, which we call the Hüttig temperature. And that's when loosely bound atoms. So if you envision a crystallite being less than perfect, there are going to be some surface atoms, there are going to be some defects at corners and edges and things like that. And when you reach the Hüttig temperature, these loosely bound atoms can actually start moving around, so leave the crystallite they're on and combine into larger chunks. And that's a lower temperature phenomenon. And part of this is what happens in this break-in period that we talked about, or I talked about earlier. So to summarize, both sintering types, both the support sintering and the active phase sintering, results in less active material. That means that there are fewer surface atoms in communication with the liquid or the gas that we need to react. So by removing or combining the crystallites into larger sizes, we end up with less active surface area. And it's not less active surface area, it's less active surface area. Finally, fouling is when we physically block an active site or indeed block an entire pore with something that makes the catalyst underneath inaccessible. And it can be done in two different ways, and you have to handle these two mechanisms in two completely different ways. So you have either something that is formed in the catalyst, which is coke formation, so solid carbon formation on the surface of the catalyst, or you have something that is entering with the gas to be treated, like metal or an ash, which can't be, so yeah, two different mechanisms. One is formed inside the reactor, the other is entering the reactor with the feedstock. Looking at the first one, the coke deposition, it's something that you can't purify away. So you can't remove it upstream with what you can do with the other type, the fouling type, and the ash deposition type fouling. And it's really dependent on what the feedstock material is. And the stability of the starting point molecule strongly influences how severe coking will be. So if we again look at steam reforming catalysts, you will see much more carbon formation on the catalyst if you try to process ethylene as opposed to benzene and toluene, which are aromatics. So if you have an aromatic, though it's even more carbon forming than the equivalent normal heptane. And the longer the carbon chain, the more carbon you're forming. So N-heptane is worse than N-hexane. But the cyclical version of the molecules, the naphthenes, are less carbon forming, as well as branched molecules are also less carbon forming than the naphthenes. And the smaller, again, the molecule, the more carbon forming they are. CO and methane. Methane is the most straightforward one to process. And the way to counteract this deactivation is working with much more steam present. So the more carbon forming material, the higher the steam to carbon ratio you need to have. Steam helps to keep the surface clear. You can also recycle part of the hydrogen to help keep the carbon off the surface. So two measures to counteract carbon. And of course, you can change your catalyst composition. Coke forming or coke deposition is, of course, a side reaction. It's usually a parallel reaction where you have A and B going to, or A product, reactant A going to B, or you can have the reactants form the coke, so A going to C, or it can indeed happen in series. So you have A going to B, where B is then transferred into the coke. And the parallel fouling will result in deposits where the reactants are the highest, so at the inlet of the reactor. Series fouling, of course, will happen where the deposits are in the highest concentration at the outlet of the reactor. And you can also see this effect on individual pellets. And here you also see interesting effects when you introduce diffusion into the pellets. So on the next slide here, we have first the disproportionation of toluene, which is a parallel thing. So it happens where the concentration of the reactants are the highest. And if you do this at 400 degrees, you will actually see an even carbon layer throughout the catalyst. But if we increase the temperature and go to 530 degrees, you will see that the interparticle diffusion limits the high concentration of reactants to the outer shape. And for the parallel case, it's the other way around. So here we do N-butyl alcohol dehydrogenation, and at 400 degrees, the concentration of the products is the highest in the middle, and that's where we see the carbon formed. But again, going up in temperature, you will see carbon formation in the outer shell because the reaction occurs much faster and there are transport limitations. Then there's a few things that are important to say about coke depositions. First of all, they're not just carbon. So they're going to be somewhere between 40 to 100% hydrogen compared to the carbon. And this is really helpful when it comes to regeneration. So if you have a catalyst that is covered by coke, you can decide to stop operation for a while and do something that we call regeneration or steaming. And by introducing steam, or indeed steam and oxygen, or just oxygen, you can remove the solid carbon again and restore at least part of the catalyst activity. Depending on the temperature, you will actually see a different behavior of the removal if you look at where you are in the pellet. So if you have pellets and you have the pellet surface here and the pellet center here, so this is a radius, and you have a certain concentration of carbon. If you do this at low temperature, you will have no influence of gradients and you will have a very even removal of the carbon all the way down. If you go up in temperature, you start seeing some gradients, diffusion limitations. You will have a sort of diagonal removal. So you have the pellet surface moving down to the center. And if you are at really high temperatures, on the other hand, you will work your way from the outer surface all the way to the center, because all the oxygen and steam is reacted before it reaches the center. And similarly, we can have fouling via deposits of impurities. It can be from hydrotreating, where you have metals in the feedstock, or indeed it can be when you treat flue gases from DeNOx, there will be ash in the flue gas that will clog your catalyst. And again, these deposits can either fall out during the reaction. So if you have organometallics, you will react these organic metals to their hydrogen counterpart and leave the metal on the surface. Or you can deposit ash via gas transport. The deposition will cause pore plugging, and of course, again, you will have part of the catalyst that is non-accessible to reactants. Finally, the poisoning or fouling can be selective or non-selective, and this is really a combination of, one, what type of deactivation you have, and two, how your reaction is occurring with respect to diffusion regime. And of course also a little on how you distribute your active phase in the material, but that is an effect of your diffusion regime. So, and then you can look and you can make three types of curves. You have one where you have A here, where you have one deactivation occurring per introduced molecule. And that is done, for instance, if you have either a chemically a surface reaction limited reaction as well as a surface limited poisoning, or you can see it also if the deposition of the poison is occurring mainly in the outer parts of the catalyst, so we're in the type an eggshell deposition. If you have mass transfer limited type reaction, you can also see the inverse, where you have much more deactivation for a little introduced poison, and that's typical when you have diffusion control systems to get this behavior. So basically, when a little poisoning on the outer will do a lot of damage because, yeah, of the reactions occurring, or the reaction regimes with respect to diffusion. And also, finally, you can have anti-selective poisoning. If you, for instance, have uniform poison distribution, but you have reaction only on the outer part, or indeed if your poisons concentrate to the center and you get diffusion control reaction. So to conclude, deactivation is crucial to operation economics. So the longer you can run your reactor, the better. Three main types: chemical, thermal, and mechanical, and they're mainly caused by temperature, impurities, or by side reactions, and all types of poisoning can be selective or non-selective depending on the diffusion regime that you're operating in. Further reading: Deactivation of Catalysts and Catalyst Poisons, that were both released in 1984, 2 books, good year for catalyst poisoning. And there's also a nice summary of the mechanisms of catalyst deactivation in Applied Catalysis from 2001 that I strongly recommend. And with that, I would like to thank you for your attention. And as always, please let me know if you have any questions and I'll do my best to answer them. And with that, I wish you a good day. Thank you.